Having established that units are exactly those elements with norm plus or minus 1, in 136, we're showing that the only units in z adjoin square root of d when d is less than or equal to negative 2 are plus minus 1. We can't get any more interesting examples. On Tuesday, we saw an interesting example in z adjoin the square root of 6. If you recall, we had this element, z equals 5, plus 4, plus 2 square root of 6. I think that's what it was. And we showed that this was a unit. And how we showed that it was a unit is we showed that z conjugate, its inverse, or its conjugate rather, was its inverse. And the reason that we could do that is what was the norm of this element? It was 1. 5 squared minus 2 radical 6 squared. So we could do that, but this is an answer to the question, well, what if we change this parameter over here? What if instead of the square root of 6 we adjoin something else? And according to this result, if the thing underneath that radical sign is less than or equal to negative 2, then we can't get any more interesting units in that ring, that we're restricted to plus or minus 1. So how'd you do that, 136?
Well, first of all, we know that from proposition 27, the units of z are equal to plus minus 1.
Okay.
So we need to show that. So then what we wanted to focus on was the units of z joined with d are equal to the units of z.
Okay, so this part you didn't have to prove, but that part you had to prove.
Set container.
Okay.
So first we said what is z be an element of the integers in radical d.
Okay. I'm with you. Keep going.
Then z is equal to a plus b radical d, where a and b are integers.
A plus b radical d. All right.
And the normal of z is equal to a squared minus db squared, which has to equal 1.
Okay. How do we know it has to equal 1?
From 135.
From 135. Okay.
Now, because d is less than or equal to negative 2, we can say that a squared minus db squared is equal to a squared plus the absolute value of db squared.
All right.
And then we actually used a contradiction. So we said, let's assume that b is not equal to 0.
All right.
Then absolute value of db squared has to be greater than absolute value of d.
Absolute value of d b squared must be greater than absolute value of d.
Which is going to be greater than or equal to 2.
Okay.
So the norm that we're going to get is a squared plus absolute value of db squared is going to be greater than a squared plus absolute value of d, which is going to be greater than a squared plus 2.
So absolute value of d, which is greater than a squared plus 2. Okay.
But since that's supposed to equal 1, that's a contradiction. Since a squared is going to be greater than 1, so you can't.
Since a squared is greater than...
A squared will be greater than 1. Greater than or equal to 1, so a squared plus 2 will always be greater than 1, and it will never equal 1. So we have a contradiction.
Okay. So if I read this from left to right, 1 is equal to a squared plus the absolute value of d times b squared. But that's greater than a squared plus 2, which actually, if you're saying that a squared is greater than or equal to 1, how do we know a squared is greater than or equal to 1?
Because a is an integer.
No, it doesn't mean that a squared is greater than or equal to 1.
So it's greater than or equal to... It's greater than or equal to 0, but
okay.
Greater than or equal to 0 plus 2 will be greater than...
That's right. So this has to then be greater than 2. So in order to accept the fact that b is not equal to 0, so this was your, this was the thing that you were going to develop a contradiction from, that if b is not equal to 0, then 1 must be greater than 2.
So that means b is going to equal 0
Right.
which makes now your z just equal to a.
Contradiction. So b must equal 0. And if b equals 0, then z is equal to a. Okay.
And so that's an element of z of x.
How do we know it's a unit?
Because then we have to say a squared is equal to 1.
Right, because the norm is equal to 1.
Yeah.
Therefore, a must equal plus minus 1. However you like to do that. Okay, cool. So that's for the containment going actually the difficult way. Right? The only invertible elements of z adjoin radical d are plus and minus 1 as integers. What does the opposite containment look like?
The opposite containment is that the units of z would be found in z adjoin radical d. So
Okay.
let lowercase z be an element of the units of z.
Okay.
Then z is equal to z plus 0 times radical d, which would be an element of z adjoin radical d,
Okay.
since z is an element of the integers.
Sure.
The normal of that would just be z squared minus d times 0 squared, so z squared.
Norm
And
of
that
z
has
is
to
equal
equal 1.
z squared. And that has to equal 1 because
Because the normal has to equal 1 from theorem 135.
135. Okay.
And so z is an element of z adjoin radical d unit.
Okay, again by 135. Okay. Thus, z is a unit in z adjoin d. Okay. Cool. Z adjoin radical d. All right. Excellent. So we can do a lot with the norm in these quadratic extensions of the integer. We can first decide whether or not one of these elements is a unit, with the norm is plus or minus 1. We can also decide whether or not an element is irreducible if the norm is equal to a prime. There's one more example that I want to surface that's going to kind of be a toehold for us into talking about irreducibility of polynomials in a more general sense. So this is the example that I want us to chew on for the rest of the hour.